Hi, I'm Bart Everson, a creative generalist here at the Center for the Advancement of Teaching and Faculty Development here at Xavier University of Louisiana. It's my honor to partner up with my boss, outgoing director of our center, Elizabeth Yoasthammer, to present to you a little bit of information about how learning works, how human learning works, but also how machine learning works. So I'm going to talk about the one, she's going to talk about the other. Now, I'm not an expert on machine learning, and so I struggled for a way to explain this in terms that even I could understand. So, of course, what I did was I had an artificial intelligence explain it to me in simple, folksy, down-to-earth language. Are you all ready to take a deep dive into the country-fried world of machine learning? Let's get this tractor rolling. Well, data's the bread and butter. Imagine data as the all-you-can-eat buffet for machine learning algorithms. They gobble up data like there's no tomorrow. But here's the kicker. If your data's as messy as a toddler's dinner plate, your algorithm's going to have a bellyache. So you got to clean up that data real nice and pick out the bits that matter most. Just like choosing the tastiest morsels from the buffet. Now, there are different ways that these critters learn. You got supervised learning. First of all, that's like the guided tour. Think of it as taking a guided tour through the bayou. You got your labeled data, which is like having signposts telling you what's an alligator and what's a log. The algorithm learns by looking at examples that already have the right answers attached, kind of like a teacher giving you the answers to study before a big test. It's great for tasks like predicting whether it's going to rain on Mardi Gras, or if that gumbo is going to be spicy. Now, unsupervised learning is like wandering in the French Quarter without a map. You're exploring on your own, you're finding patterns and groups without any labels to guide you. It's like trying to figure out which jazz band's going to make it big by listening to them play. No one tells you nothing. You just got to use your noggin to sort things out. Then you got semi-supervised learning. It's a bit of a gumbo pot, mixing a little bit of labeled data with a whole lot of unlabeled data. It's like having a few signposts, but still exploring the swamp mostly on your own. And this style can be mighty helpful when you've got a lot of data, but labeling it all would be as long as waiting in line for beignets at Café Du Monde. Last but not least, reinforcement learning is like learning to fish in the bayou. You try something, see if you catch a fish or just a boot, and learn from it. It's all about trial and error and getting rewards like a big old catfish or penalties with just a muddy boot. Over time, you get better at knowing where the best fishing spots are, just like the algorithm learns to make better decisions. Here's the thing. Machines can be as biased as a grumpy old man. They learn from data, and if that data's got a slant, well, the machine's going to pick it up too. We got to be like fair-minded sheriffs, keeping an eye out for unfair play, making sure our AI townsfolk are treating everyone square. It's a fine line between a model that's simpler than a country tune and one that's more complex than a city slicker's coffee order. If your model's trying too hard, it'll fit the training data like a glove, but won't know how to handle anything new. Keep it simple, but not too simple, like a good old home-cooked meal. Now at this point, I had to admit, I still didn't know what the machine was telling me. Remember, I got all this text from an AI. I didn't write it myself. But in this case, I found the countrified metaphors just a a little obscure, so I asked the AI to elaborate, break it down into more detail. All right, let's roll up our sleeves and dig into the nitty-gritty of simplicity versus fancy pants in the world of machine learning with a touch of detail and a sprinkle of down-home charm. Imagine you're at a country fair and you've got two kinds of pie contests. One's for the simple classic apple pie, that's your simple model. It's straightforward with just a few ingredients, and everyone knows what to expect. It's like a linear regression model in machine learning, easy to understand and explain, but it might not catch all the nuances of complex data. Now, on the other side of the fair, you've got the fancy dessert contest. That's your complex model. These desserts have layers upon layers, like a deep neural network, with all its neurons and whatnot. They can handle all sorts of intricate patterns in the data. Good luck trying to explain what's inside to your grandma. Now here's the kicker. If your apple pie, meaning the simple model, is too plain, it might not win any ribbons because it doesn't capture the rich flavors of the data. But if your fancy dessert, that's the complex model, is too over the top, it might only taste good at the fair. In other words, it might overfit the training data. And it would be too much for a regular Tuesday night dinner. In other words, it would perform poorly on new, unseen data. So what's a baker to do? You got to find that sweet spot. A pie that's got just enough flair to impress the judges, but still reminds them of the pies their mamas used to make. Well, machine learning, that means choosing a model that's just complex enough to learn the important patterns without getting all tangled up in the specifics of the examples it was trained on. And there you have it, a detailed look at the delicate dance between simplicity and complexity in machine learning, all wrapped up in a cozy, folksy package. Just remember, whether it's pies or algorithms, the blue ribbon goes to the one that best balances tradition with a touch of pizzazz. All right, now hold on there. Just one more thing about machine learning. You know, it ain't just about computing. It's a hoedown with math, statistics, and a dash of whatever special sauce your field brings to the table. So encourage your students to be like bees, multidisciplinary bees, buzzing around different fields to make the sweetest honey. That's enough from me. I'm going to kick it over to the boss lady, Elizabeth Yost Hammer, who's going to tell you all about human learning.
Hi, Elizabeth here. Now let's talk about how human learning works. And I'm going to base a lot of what I'm talking about on this book, which talks about 7 research-based principles for smart teaching. I highly recommend it. The first principle of human learning, and this is one of the most basic and foundational ones, is learning must be built on prior knowledge. It's how our brains work. It's how we take in new information. We have information that we already know, and then we encounter new information and we place it into our schemas that we already know and we build on that. So knowing this, it's really good to activate prior knowledge for students. If you're about to do a complex topic, ask them, what do you already know about this topic? Have you heard of it? Anything to activate their prior knowledge so that you can then build on that as you move forward. And a lot of these recommendations came from the Teaching Center at Florida International University. The second principle: expert and novice learners differ primarily in how they organize knowledge. So that's back to kind of building on prior knowledge. To be an expert, what happens is you have this whole network of information in your discipline. Say you're a biologist, you have this whole network of biological concepts and terms and theories that you can plug that information into. Whereas a student who's a novice just learning it, they might learn it as these independent, different pieces of information and not see how things are connected yet. So to get students to move up and organize their knowledge the way an expert would, you should make explicit connections for them. Help them do that. Be explicit. And then use kind of various and contrasting examples so that students can see, oh, this is how this information is connected. And then again, then they can build on those connections. The next principle of human learning is that students' motivation determines, directs, and sustains what they do to learn. And we know this, right? The motivation a student brings into the classroom um, and determines their engagement with the class and their learning ultimately. So, but what can we as instructors do to enhance student motivation? Well, the first thing we can do is provide authentic tasks, okay, authentic assignments for them. In the age of AI especially, I think we're going to need to provide students with assignments and tasks that they can really see the long-term application of, right? I mean, if it's just going to check off something for our class, why wouldn't they? Why wouldn't they use AI to do this, right? But if this is something where they see the value of it for their lives, for their well-being, for their careers, for their next step, okay, graduate school, medical school, whatever, they can see the value of it, then that's a different story. So we're going to have to really look at our assignments and see, are these authentic? Do they have long-term value in our disciplines? Then we can also share our passion with students. Like, you're passionate about your disciplines just like I'm passionate about psychology, and we should share that with students so they can see the joy in learning and the value in learning. And then finally, and this is a big one, is we should be transparent. Transparent in our assignments with students. We should share the purpose of every assignment with them. Be explicit with the purpose, because we've thought about this purpose and we know it's authentic. So now we want to share that with them so they can see the learning that they should have and then be more motivated. We should also share the steps of the task, make this task very clear for students, right? What do they have to do this task or this assignment? Again, so that they know what's expected of them and they can be motivated to do it. And then finally, we should share the criteria for success. That's what transparency is. For every assignment, you share the purpose, the actual task, okay, very clearly, and then the criteria for success. And the data shows that's really important for student motivation. Okay, the next principle is that mastery of material is complex and it takes time and it takes practice, right? We've mastered our fields, wow, over not just our graduate school, but over the course of our careers, right? Mastering this takes time, but it also takes practice opportunities. So we should recognize the cognitive load that our assignments, our disciplines, our readings should recognize the cognitive load that this places on students and take that into account as we kind of make the rhythm of our syllabus and the rhythm of our assignments. Okay. And we should also provide plenty of practice opportunities. Again, in the age of AI, we know that providing a lot of these formative assessments instead of one big summative assessment is going to reduce the reliance on AI. Even if we use AI as an aid in an assignment, it would reduce that dependency, right? Because it's building up to assignments. So provide plenty of practice opportunities. Again, this is how humans learn, and so we need to take that into consideration. Human learning is also, we know it's goal-directed. Okay, goal-directed. And goal-directed practice coupled with targeted feedback enhances the quality of student learning. Yeah, we have to know what our goals are and set this for students, but then we have to provide targeted feedback over time for students so that they can learn and they can move forward. The thing you can do for this is use rubrics. Okay, you can use rubrics, and we can embed rubrics in Brightspace here at Xavier. Rubrics help students see where their grades coming from, what your priorities are, and can help them know, okay, this is what I should be focusing on. Provide excellent and bad examples of tasks and assignments. Okay, again, that builds on students' prior knowledge. If they can see, oh, this is what she's asking of me. Okay, this is how I understand this. Then I'm starting at a different level, and I'm able to kind of move up to where you want me to be. And then give feedback only on your priorities. This is a weird one, but I think oftentimes I'm going to say this, oftentimes when we're grading, we might give a lot of comments on things that it's easy to comment on, like grammar, or in my case, APA style, and not so much comments on the big thinking that I really want students to do. Well, if we do this, then what happens is students think, oh, grammar and APA style is the priority here, not the real objective that I have for students. So think about it. We might need to give up some of those comments that are not our priorities, maybe early on, to get students to focus on our priorities and direct them in this goal-directed way. Human learning is also related to students' current level of development. Okay, we know that their level of development interacts with the social, emotional, and intellectual climate of our course, and all this shapes learning. So things we can do here, we need to normalize uncertainty in our classroom. Model it for them, right? Model this. We need to model respect in our classrooms. We need to have inclusive classrooms that have multiple and diverse examples. Okay, because again, students bring their own developmental, developmental stages, wherever they are developmentally. They're bringing this into the classroom. And we're seeing this change over COVID. We're going to see it change, as we now are getting out of that kind of COVID classes. So we need to be aware of that and aware of what our students are bringing. And then finally, to become self-directed learners, okay, which is what we want students to do, take what we've taught them and take it to the next class and beyond, right? To become self-directed learners, students must learn to monitor and adjust their approaches to learning. That is, they must develop metacognitive skills. They need to know what they know and what they don't know so that they can move forward in their learning. And so in order to encourage this, you need to be more explicit than you think over and over. You need to be more explicit in your assignments and your expectations and your grading criteria, in the purpose. Okay, why this class? Why this topic? Why are you doing things the way you are? Don't teach behind a curtain, so that students think it's magic. Be explicit. You also need to provide times for students to reflect on their own learning, right? The only way we build skills is through time and practice, right? That's how we master different skills. So provide opportunities for students to reflect on their own metacognitive skills. Allow them time to think about their own thinking, learn about their own learning. And so allow for evaluation of these skills as well. Ask students to evaluate them, and then you can come back and give them feedback on that. All right. So yes, we're moving to an AI world, and that's the topic of the resources we're providing you. However, we're still teaching humans, and we have to be aware of how humans learn so that we can have authentic learning in this AI world. Thank you.
All right, let's wrap this up. Thank you, Elizabeth. Some key differences between the two types of learning, between how machines learn and humans learn, right? Number one, learning performance. Humans tend to perform similarly across different patterns, while machines show large performance differences depending on the patterns that are involved. Humans tend to reach a plateau in performance after seeing a certain number of instances. It could be due to cognitive overload. But machines learn slower, but can eventually reach or even outperform humans in certain patterns. Number two, data requirements. Machines require more instances compared to humans to achieve the same results. Machine learning models are best suited for situations with lots of data. We're talking about thousands or maybe millions of examples. Number three, accuracy and reliability. Machine learning models have been found to be more accurate and reliable than human classifiers in certain tasks, like, for example, classifying scientific research abstracts. While the top percentile of human classifiers can outperform machine learning in limited cases, training such classifiers is costly and is difficult compared to training machine learning models. Number four, the approach to learning. Humans learn through experience and feedback, similar to how machine learning algorithms improve through trial and error. However, machine learning primarily relies on algorithms that learn from and make predictions based on data, while while humans use more complex cognitive processes. And finally, generalization, number 5. Humans tend to perform similarly across different patterns, while machines show large performance differences depending on the patterns involved. Humans can generalize learning to new situations, while machine learning models are often specialized for specific tasks. In summary, then, machine learning differs from human learning in terms of learning performance, data requirements, accuracy and learning approach, and generalization ability. While both leverage patterns and data, machine learning is more specialized and data-driven compared to the more flexible and experience-based human learning. Got that? Cool. Thank you for your time and your attention. This is Bart Everson signing off.